Hey everyone! Imagine flipping a switch on a machine the size of a fridge, and in just 200 seconds, it finishes a task so enormous that the world's fastest supercomputer would still be grinding away when your great-great-grandkids' are long gone. 10,000 years. That's not hype. That's what happened in a lab in Santa Barbara. But here's what keeps physicists up at night. No one can fully explain where that calculation actually took place. Not in the hardware, not in our universe as we know it. What if these machines aren't just faster computers? What if they're quietly proving that reality itself is far stranger and more connected than we ever dared imagine? Stick with me. Today we're diving deep into what quantum computers like Google's Sycamore and Willow have actually shown us about the fabric of existence. I'll share fresh analysis on why this isn't just engineering wins, but a philosophical earthquake. We'll unpack real human stories behind the breakthroughs, explore mind-bending implications for your daily life, and end with a powerful takeaway that could shift how you see every decision you make. If your mind is even a little curious about the universe, hit that like button and let's explore why this might be the most exciting and, yes, a bit unsettling moment in human history. Let's start with the jaw-dropping results that first cracked the wall. Back in 2019, Google's Sycamore processor with just 53 superconducting qubits ran something called random circuit sampling. Sounds nerdy, right? But it proved quantum machines could do in minutes what classical systems couldn't touch in millennia. IBM pushed back hard, claiming optimized classical tricks could shrink it to days, but even they admitted the gap was real. Fast forward to Willow in late 2024. This chip didn't just compute faster, it showed something revolutionary. As you scale up the qubits for error correction, the whole system gets more stable. Think about that. In every car, power grid, or phone you've ever owned, more parts mean more ways to fail. Entropy wins. But quantum error correction below a certain threshold flips the script. The noise cancels itself out exponentially. From my perspective, this isn't just clever coding. It's a direct challenge to how we think about complexity in the real world. We've spent centuries building things assuming bigger equals riskier. Quantum hardware says, not if you're tapping into deeper rules. I remember reading early critiques and thinking, this feels too good to be true. But the data keeps coming. These aren't simulations, they're physical demonstrations that our classical intuition about where work happens is incomplete. Now let's make this personal with some human stories that bring the science alive. Take Hugh Everett III, the Princeton grad student in 1957 who proposed the many worlds idea while wrestling with quantum mechanics' infamous measurement problem. You know the drill. Particles exist in superpositions until observed, then collapse. Everett said, what if the math is literal sols, no collapse, just branching realities for every possibility? His advisor, John Wheeler, loved it. But Niels Bohr's Copenhagen crowd shut it down hard. Everett's full thesis got chopped. He left physics for Pentagon work on nuclear strategy, battled depression, and died young, at 51, in 1982, never seeing his ideas revived. Fast forward. Today, hardware like Willow aligns eerily well with what Everett described. I can't help but feel the tragedy and triumph here. One man's fringe idea, dismissed as unprovable philosophy, now gets indirect support from billion-dollar labs. It's a reminder that science isn't a straight line. It's full of brilliant minds who plant seeds in rocky soil. Another vivid example, the Chinese Mikias satellite team in 2017. They entangled photons and beamed them to ground stations 1,200 kilometers apart across the planet. No wires, no signals, just correlations holding strong through atmosphere, weather, and relativity. Imagine engineers in a control room in Beijing watching data confirm entanglement over distances wider than some countries. That wasn't theory. Now, it was a real satellite proving quantum links don't care about distance the way we do. It hits different when you picture the late nights, the rocket launches, the quiet high fives, human perseverance meeting cosmic weirdness. Let's zoom into the math that forces these wild conclusions without getting lost in equations. A classical bit is 0 or 1. Add qubits in superposition, and 2 represent all 4 states at once. Scale to 300? You're talking 2 to the power of 300 possibilities more than atoms in the observable universe. A quantum computer doesn't visit them one by one. Interference lets it navigate the whole probability landscape simultaneously. Where does all that information live? Not in the 105 physical qubits of Willow, not in any single chunk of matter we can point to. This is where David Deutsch's 1985 paper lands like a thunderclap. He argued quantum computation requires parallel realities, the many worlds view, because no single universe has the physical resources. As one GLASP-highlighted discussion of Deutsch's work notes, taking the quantum equation seriously leads straight to a multiverse, where everything that can happen does happen. Thinkers like Naval Ravikant have echoed this, connecting it to decision-making. Every choice branches realities in ways that reshape how we view probability and regret. In my analysis, this isn't sci-fi. It's a practical implication staring at us from lab benches. If true, your what-if moments aren't just mental. Infinite versions of you are living them out. Terrifying, maybe, but it also makes every choice feel cosmically meaningful. The 2022 Nobel Prize sealed the deal on non-locality. Experiments by Aspect, Clauser, and Zeilinger proved Bell inequalities violated no local hidden variables. No classical under-the-hood explanation. Entanglement is real, and it's non-local. Then there's the ER equals EPR idea from Maldacena and Susskind. Entanglement might literally be tiny wormholes, making space-time itself emergent from quantum connections. John Wheeler's It from Bit takes it further. Reality at bottom is information processing distinctions, not stuff. Experiments confirming Landauer's principle, erasing a bit costs real heat, back this up. My take: these ideas converge on one insight. Classical physics assumed a local material universe. Quantum tech shows us something richer, an informational, relational cosmos. We're not breaking physics, we're discovering its deeper operating system. Down on Earth, this hits your wallet. Shor's algorithm means quantum machines could crack today's encryption. That's why NIST raced out post-quantum standards. By 2024, governments are already swapping algorithms because of harvest now, decrypt later threats. Imagine your old bank transfers from 2023 suddenly readable in 2035. Scary, but also driving innovation. Pair it with AI. Quantum hardware could supercharge matrix ops in neural nets via algorithms like HHL, potentially slashing training costs. But here's my fresh analysis. When opaque AI designs quantum circuits we can't fully simulate, we get double black box systems. Real-world risk? In drug discovery, a quantum AI model might spit out a miracle molecule we trust without verifying every step. We've seen AI hallucinations. Scale that to quantum, and you need new trust frameworks. Microsoft's push on topological qubits, Majorana modes, offers hope encoding info non-locally, so local noise can't touch it. If it scales, fault-tolerant machines arrive decades sooner. Story time. Picture a researcher at Microsoft staring at data from their 2025 Majorana 1 chip, realizing the protection isn't shielding, it's geometry itself hiding the info. That's the kind of aha that rewires careers. Finally, this loops back to Nick Bostrom's simulation hypothesis, but quantum makes it weirder. Simulating our entangled, non-local universe on classical hardware is impossible. The simulator would need quantum resources too. The hierarchy collapses. We're not in a sim so much as part of a self-consistent quantum fabric. So what's the clear takeaway? Quantum computers haven't proved a multiverse in a courtroom sense, but they've forced us to confront a reality that's non-local, informational, and vastly bigger than one universe's atoms. The terrifying part isn't the strangeness, it's our old maps failing. The empowering lesson? Lean into the unknown. Every breakthrough from fire to flight came when we built tools that outran theory. These machines are doing it again. Stay curious, support ethical development, and remember your choices might echo across branches. The universe isn't just running, it's computing with us. What do you think? Multiverse or deeper layer? Drop it in comments. Like, subscribe, and I'll see you in the next one, wherever that branch leads.